All right, so let's have a little bit of fun. We all love to play pool, so let's look at a billiard ball as it hits a railing. All right, so it's going to come down and hit a railing, and then we're going to calculate the coefficient of friction. So we're going to figure out what the friction is. Now, why do we care about the friction on a railing? Well, think about it this way. You have your ball. It's going to come on down here and hit the railing, and then it's going to bounce off. So what's the physics there? Well, the physics is basically that there's some force here from the railing on the ball that's going to be a normal force, but that's going to act basically like a spring. It's going to be acting like a damped spring. So we've talked a little bit about what happens in that already. You've seen a little bit about what happens in that already. So that is the basic physics. On top of that, there's going to be a little bit of friction this way when you rub the felt against the ball. So the railing's rubber covered in felt. The rubber is going to provide this normal force with a sort of a spring-like force on it. We're not going to care about the normal force as such. We're going to care about sort of its average force. So we don't have to worry too much about it, and we can look at an average frictional force as well. That's not going to matter too terribly much, of course, because the frictional force is equal to mu times the normal force. So that mu is going to be constant the whole way through. So we're not going to have to worry too much about some of the specifics. One of the specifics is exactly a good model for the normal force. We don't have to get a really good model for that. In this particular problem, we can just think about it as the normal force is proportional to the frictional force, and that should be sufficient for us. On top of that, we probably aren't going to have to worry about the interaction time. That's good because I couldn't find the interaction time online for the ball and the railing. Normally, that's probably going to be a few milliseconds. That's really, really a short time. I mean, we've all played pool. We know that it doesn't just sort of sit there at the railing, the ball. It just hits and goes its merry way. So we'll just look at it in that sort of model. So again, let's try to draw it a little better, a little nicer. So I'm still having trouble with this. So I was talking to somebody and they were saying that probably this is all because I'm not used to working on a surface without any friction. I've done this a few times. I've never been happy with my handwriting on them. So we've got the ball that's coming in at a speed v. That's normal, and it's going to come out over here at a speed v over 2. It's going to come out at half the speed. Usually the numbers, of course, that I'm going to use are there to make things simple. So you might ask, well, then why did I use some horrible number like 53.1 degrees here and another equally horrible number, 36.9 degrees? Well, if you've had these things beaten into your head, which you probably have not, those are the 3, 4, 5 triangle angles. And so this is actually a very special case where this is a perpendicular right there. So, 53.1 plus 36.9 is 90 degrees, and this whole thing is 180 degrees. So, the two paths are perpendicular coming out of there, even though it's off kilter a little bit. It's not really perpendicular to, it's not really on this y-axis, this perpendicular. It's off a little bit, but that's okay. So those are the things we have. So let's see, we have a speed in both cases. We already have both cases, the speed and the angle. This makes things pretty interesting. This makes it so that we have to look at the interaction instead of at the results of the interaction. So I think that's going to be true for the collision problem on your group homework. It's been a little while since I worked it, so I don't know, but I think I gave you, even if it was a little bit tricky, the way I worded it, I think I gave you a situation where you should know all of the initial and final speeds, but I don't remember. Maybe you need to find one of those things. What was it? What was it I asked you on that? Oh, that was the relative speed of the two or the relative velocity of the two guys. That was pretty close, pretty good. Oh, I'm doing the same thing over. See, that's why I shouldn't think while I'm doing things. It's always bad to think. Always do what you had in mind. Got a mass M, and these are all for the ball. I should have written that first. What do we know about the railing? We don't need to know anything about the railing. Like I said, we don't need to know about the interaction time or any specific constants of the interaction, which would include like a effective spring constant or a Young's modulus for the rubber, and then some other stuff for the felt. We're going to figure out something about the felt, which is the coefficient of friction. Okay, so is that it? I think that's all I actually need for this, or at least at this time. I mean, that might change a little bit later on. Let's see what we see. All right, so what is the concept for this? Well, we're going to use impulse. So why would we use impulse? Well, this looks like a collision, but it's actually a deflection. So what's the big difference between that? The difference is this wall does not move, right? So because that wall does not move, its momentum doesn't really change. Now, you can think about it as in terms of, you know, what's going on internally inside of the rubber, and the momentum of the atoms actually does change. There is sort of a, well, I don't know what they call it for rubber, because that's a polymer, I think. But if you're looking at a solid, right, if you're looking at something like iron, what you'd look at is the crystal momentum. There's a sort of a momentum in the crystal that's very important, and anytime you hit something with it, you know, that stuff goes in there. So there is momentum inside of the object. It's just something that you can't really look at. It has to do with you know, the sound propagation and, you know, atomic vibrations and stuff to do with electrons moving around, and all of those different interactions can carry momentum. So there is momentum inside of things, but we sort of abstract it out in this case. So unless you want to do a giant sum over all of the atoms of the rubber, let's just use the impulse for this case. And the impulse has a definition. The impulse, which is an I with an arrow over it, is equal to the net force on the object times the time that that net force is applied. So we're just going to use the average forces on this in this case. So that's what we're going to do. So we don't really need a Newton's second law thing or anything like that. But we do, just like we need for the work, a free body diagram, because we care about the net force, right? The net force, we said, is going to go up a little bit from the normal force, right? The normal force is going to go this way. There's going to be a frictional force that way. So the net force is going to have to come along this diagonal. That's your net force. So this is really close to the edge. Net there. We have a normal force there. That's the average. And a frictional force there. That's an average. And this is the x direction, and this is the y direction. We're looking down at a pool table, so we don't have to worry about things like weight, because the weight's going straight down. We don't care about that. The normal force from the surface of the billiard ball is coming straight up. We don't really care about those things. It's not that much. That's not really very important. I don't want to see anything where you're trying to draw cubes and stuff in 3 dimensions. That sort of gets rid of the whole purpose of the free body diagram, which is to simplify things so you can look at the physics rather than looking at sort of a picture of the situation. Look at the interactions where the physics is, right? Because the physics lies somewhere between the things we see and the mathematics we use, right? So the physics is right in between there. And I think we're ready to get to the physics, right? So the next step here is going to be our plan, and that's our physics, as we've said, and then we get to our execute, and that's our math, right? And remember, this is 22 points This is 6 points. As long as you're doing reasonable math, you're not going to lose too many points. Let's see, where do we go? Okay, we need a plan. How do we start this? Well, we want to find the coefficient of friction mu, right? That's where we start. And at some point, we want to get to the impulse. We need the definition of impulse in there. So those are the two things we know. There's only really one way to find the coefficient of friction, right? When you're looking for the coefficient of friction, you need the definition of friction, right? The definition of friction is just that the friction is proportional to the normal force with the coefficient of friction as the proportionality constant in the perpendicular direction. We've already taken care of the perpendicular part in that physical analysis there, so we don't have to worry too much about the vector there. We will worry about it in just a moment, but not quite now. Now we need question marks for the frictional force, which is an average, I think, and the normal force, which also is an average. We'll see what I wrote later. So let's see, we've got mu, and we need the frictional force or the normal force. Which one should we go for? Well, in fact, if I use the definition of the net force, right, which is just the sum of all of the forces, right? So if I use that definition, then in the x direction I have a force minus F bar. Actually, it's F bar in the minus x direction. That should have been a hat. I guess that's where the friction shows up in this thing. It should have been x hat, but without the friction, it's faster. All right. There's no friction on the tablet, so that's an issue. So, and then we have the normal force on top of that in the positive y direction. So that's the second equation. And so I get both of them in one equation. Shouldn't I only do one? Well, actually not really, because this is a vector equation. It's a vector equation in 2 dimensions, which means I can actually cancel out 2 things. It stands for 2 equations, one in the x direction, one in the y direction. So that's a little bit tricky. I've talked about it once or twice here and there, but it's never been pretty explicit this semester. It usually gets explicit somewhere around now, unfortunately. So let's see. What we need to do now is we need to somehow figure out what this F net is, right? So we need a question mark here. That got rid of these 2 question marks. So we're doing things pretty linearly. We don't have any branches thus far. Let's see. How would we find the net force? Oh, look at this. We don't need Newton's second law or third law. We just need this definition of impulse. So let's use the definition of impulse and try not to go too fast. And that's going to say F net is equal to, nothing. This is I. Crap. Okay. I, the impulse, which we don't know, is equal to the F net that we want to know, there, times the t. The time of that t is going to be the time of the interaction, the time at which this ball is right here at the railing before it comes off in this other direction, right? So that time, we're going to pretend we don't need to know. We're going to guess we don't need to know it. In fact, there's more to that. There's more to this that we could have said we don't need to know if we wanted to. But the time we're going to pretend we don't need to know. In fact, we don't need to know it. So then we'll go on to 4. 4 would be to find the I, so because that's the only guy left now. And we'll use the impulse momentum theorem because we know 2 things. right? We know the mass, and we know the velocity in either case, before and after the collision. So since we know the velocity before and after the collision, since we know the mass of the object, or the deflection, excuse me, not the collision, then something like the impulse momentum theorem, which is just saying that the impulse is the difference between the final momentum and the initial momentum, that means that we're going to be able to figure out these two guys, because that's just velocity times mass, and we have velocity times mass in both the initial and the final condition. So we should be perfectly okay. So we just have to write those. So those are both going to come from, well, we could call this the definition of momentum, right? Because it's going to be, what do we use? PI, let's say, the initial. That's going to be the mass times the velocity, right? Which is v times the unit vector, right? So we're at a point where we can just construct these things. So what is the unit vector coming in? Well, it's going to be, it's a 3, 4, 5 triangle, we said. So that means that the sine of that, the 3/5, is in the x hat minus 4/5 in the y hat. And we don't really have to justify that mathematically, because we can see that physically just looking at the geometry, that this is the short side and this is the long side. When we come back out over here, this is going to be the long side and this is going to be the short side. So that's one way to do this. So that's one way to find the momentum there, would be with the definition of momentum. Actually, the definition of vectors would be just as good. Now, why would the definition of vectors be just as good? Well, the momentum is equal to its magnitude, which is the mass times the speed, times the unit vector, which is its direction, which in this case is now going to be 4/5 in the x direction plus 3/5 in the y direction. So we could have done that separately. We could have done that through lots of different steps as well. But, you know, just to write something like this, it doesn't mean that much. So let's see what we've got here. We've got PI here. We've got PF there. So we don't have any more question marks unless we made some more. But we know the mass and we know the velocity. And I forgot this is divided by 2 because it's the final velocity. But yeah, that changes the problem quite a bit if that happens. I'm not sure if it works if that happens. So then we have all this stuff going on and everything seems pretty good, right? I think we're okay with that. So we found everything. So we just start by looking at what we want to know and say, well, what can we know about what we want to know? What can we know about what we have later and later and later and later? And we go through and do some stuff. Probably the most interesting part was this part. But this is definitely a use of the impulse momentum theorem, something that everybody loves. Okay, so there it is in white and black. So you might have noticed that I use the black on white, or the white on black instead of the black on white. I just like it so much. The text comes out just a whole lot cleaner, I think. Now, that's because I grew up when computers were always with a black background. At some point, they changed their mind. I don't really know why. Probably because of Steve Jobs. Steve liked to screw everything up. All right. But, you know, the Apple II had... I think it was the Mac that was the first one that I saw that had a white background. I'm trying to think if that was true. Anyways, so the first thing we're going to do is we're going to plug these guys in here, right? And so that's not too terribly difficult. We have an MV, right? So we're definitely going to have the impulse is equal to something times mv. Now, sort of the difficult thing here is to say, okay, well, what am I going to do? Well, what I'll do is I'll pull out the denominators. So this is 3/5, this is 4/5, this is 4/5, this is 3/5, this is a 2 there. So I'm going to put everything over 10. And then I'll just have whole numbers in the vector part. So we'll have magnitude, well, but that's not going to be the magnitude because, obviously, this part here is not going to be a unit vector because it's going to have whole numbers as entries. So I'm going to keep the directions here with whole numbers just to make my brain work easier. All right. So in this case, we're going to have PF minus PI. So that's 4/10 minus 3 times 2, which is 6/10. So that's minus 2/10. Tenths are out here. So I have minus 2x hat. Then I have 3 halves, or 3/10 minus minus 4/10, 4/5, which is minus 8/10, excuse me. So that's plus, so those numbers add because a minus is a plus. So we end up with minus, or plus 11 y hat. So that is the impulse. That is basically the change in the momentum of the object as it goes through the deflection. I hope you couldn't hear that. But I have been talking for 21 minutes without a drink of water, so I needed one. All right, so let's see what we've got. We now have to substitute something else. Well, I want to take this guy and get him into 4. Right, or into 3 here. I want to get him there. So that's good. And as long as I'm doing that, I may as well pull number 2 in that. So I make A and 2 go into 3. All right, so that'll be, whatever I've got here is actually equal to this stuff times t. So we have minus f x hat plus, it's a bar, plus n bar y hat times t. And I'm almost done, so I may as well just substitute 1 into b. Okay, well, I should keep track of these. I did 6 and 5 and 4 and 2 and 3 and 1 and a. And now B. So actually I'm doing pretty good. All I've got to do after I do this is to play around with the math. So we don't do a lot of math in physics class, but this is some point where we're going to have to do a little bit of math to make things work. So far we've just been substituting things in over and over and over again. Trying to manipulate things and to put all the physicsy parts together. And we've now got this guy here up on top is with A is equal to this thing on C. So now I have to do something with that, right? And what I'm going to do is I'm going to break this into components. At some point you're going to want to break these things into components so you can do some math on them. Not necessarily, but you can. So I'm going to solve for mu in the x component. So that's going to be mu. Got minus signs. I can get rid of the minus signs. Is equal to 2 over 10 times mv over n bar t, I think. So I have to divide through by that guy. Okay, that's all right. So let's solve the y component similarly. Why would I want to do this? Solve the y component similarly? Well, there's no coefficient on that y hat, so that's just a 1, right? That's 1 times y hat. And then I have this 11 divided by 10 here, funny number, times this mv over n bar t again. Now, that's the whole reason why I wanted to do that, right? Mu is a pure number, so when I divide d by e, I get mu is equal to, I guess I could substitute as well if I wanted to, 2/11ths, right? Because the mv over 10nt is a common, right? So the only differences are the 2 and the 11. Weird. So that's my answer. Mu is equal to 2/11ths, like 0.18 or something like that. That's pretty cool. All right, now we have to check these things, right? We love checking these things because checks are awesome, right? Actually, we like to check these things because practicing checking things is how we get used to checking things while we're working on something, right? Uh-oh. Thought I got all the little bugs. So, you see, there you go. You always check on things while you're working on them. So we want to know if this makes any sense, but we also want to know as we're working if things make sense. Now, you don't have very complicated problems in Physics 1. You don't have integrals that take 3 pages like you will in about a year and a half, okay? But when you do have problems that take 3 pages of algebra and calculus to figure out, it's good to know if you made a mistake halfway down page 1 that you made the mistake, right? Because then the rest of it's wrong, right? The rest of it's just useless. So you have to get used to checking things as you go through, not just looking at the answer and being happy with it. So it's just a state of mind you have to get into. And the tricks that I've given you are useful for that. So the tricks are, first we want to know what the symbols are in here. There are actually no symbols, right? But if there are no symbols, that's okay. It could be that this problem was perfectly determined and there's no excess to it. You don't end up with any dependencies, and that's actually true. I could have put an R in front, an R or something, a reduction factor in front of the V. In fact, I did that in the first version of the problem and decided it was too ugly. But I'm sorry. I mean, maybe you would have liked that a little bit more, but I mean, it wasn't really pretty. Okay, I could have put a different angle in there or something like that. There are ways I could have made this a little more general, but they aren't very pretty, and they don't get the place where you want to go. I prefer pretty if I can find it. All right, so let's see what we have here. Now we go to the dimensions, right? And the dimensions are, well, those are just numbers. So the dimension of a number is just 1, right? It's no dimensions, the dimensions are 1. No units, dimensions are 1. So, right, this is not going to be very informative. You say, well, my dimensions of a number are 1. So that's good, right? We wanted dimensions of mu to be 1. The dimensions of this number are 1. Everything's okay. We're all perfectly fine with that. Mu is just a coefficient. It takes a force to a force, right? Force. So you multiply this guy, he better have no dimensions because this guy's got to be in newtons and this guy's got to be in newtons, right? So we're okay with that. So that's more or less what we needed from this. I don't want the end. I'd still like to talk to you a little more. I miss you. I haven't seen you for so long. I mean, we've had the spring break and then an extra double bonus break. And now, you're off in the far corners of the globe and I'm just talking at a little tiny tablet by Samsung. So, what do we need for this? Well, not too much. I mean, this is a fairly interesting problem. I think it's good to look at stuff like this. Did we really have anything that was tricky? I think the trickiest part was this part. I mentioned that a couple of times while I was doing it. That is, when you have a vector, you basically get as many equations out of it as you have you get as many equations of it as you have dimensions, right? So this is a two-dimensional vector, so we can solve two scalar equations. Now when you come down here, we only get one arrow because we're looking for a vector, and this is a vector equation, right? So we get, instead of having two arrows, we only get one because it's a vector equation and we're looking for a vector, right? So as long as that's happening, we can't really work out too much with that. So you get two scalar equations here because it's a two-dimensional system. There's actually a third dimension, but nothing's happening there. And then here we have a vector equation, so we just deal with the vectors. So vectors are very important. You know, we see a little bit about them here in Unit 3, but in Unit 4 and Module 4, they're going to get really, really prevalent, all right, which is the reason why I keep pushing them, right, because I want you to think about the vectors a lot, all right. All right, so where are we? I think we are done. There's nothing more here. I would hope that everything's comfortable, at least where you are, and I hope that you stay safe and nothing horrible happens. All right. So, yeah, be safe, and I will talk to you again soon. Bye now.